Monu Kumawat.
Hello all, I am Monu Kumawat. Welcome to conference talk on trends in transmutation and hydride formation in brass, bronze, solder and silver brazing alloy cathodes in light water electrolysis. The work is done by Monu Kumawat and group from IIT Kanpur, India. First, we start with the motivation of our work. Recently, it was reported that alloy cathodes in light water electrolysis show transmutation, and alloys are more effective than pure metal in transmutation. Motivated with these phenomena, we study transmutation in brass, bronze, solder, and silver brazing cathodes after light water electrolysis to see if alloys perform better than pure metal samples for transmutation studies. We perform an experiment to investigate whether an electron beam on metal hydride can give rise to transmutation, and some studies motivate us about possibility of stable superhydride. For this, we also report thermogravimetric analysis of electrochemically prepared hydrides. Experimental setup. Figure 1 presents our experimental setup of light water electrolysis. There are some important components of our setup, which are DC power source, beaker that have composition like that. Electrolysis solution, we always take 1 molar aqueous potassium carbonate. Counter electrodes, we use high quality graphite with 99.9% purity in all our experiments. Cathodes alloys. In left side of figure 1, there is the side view of electrolytic cell in which we can see evolution of oxygen and hydrogen at anode and cathode respectively during electrolysis. Let us look the transmutation results now. This slide shows the EDS analysis of silver brazing cathodes. Electrolysis of 1 molar aqueous potassium carbonate is run 30 volt with 5 ampere per centimeter square current density for 10 hours. Figure 2 presents the elemental composition of silver brazing before electrolysis, and its EDS analysis shows that it consists of silver, copper, cadmium and zinc. Yellow with brown color refers silver, blue color shows copper, orange refers cadmium, and zinc data are in red. In right side, figure 3 provides the composition of silver brazing after electrolysis. Comparing both figures, the sample gets a transmutation in terms of 6 to 7% iron in yellow bar that is not present in initial sample. Let us look at transmutation results of brass alloy. Electrolysis of 1 molar aqueous potassium carbonate is run at 33 volts 5 ampere per centimeter square current density for 10 hours. Figure 4 provides the original composition of the brass, which is copper and zinc. Blue bar refers copper and red bar presents the elemental composition of zinc, whereas figure 5 shows the EDS analysis of reacted brass. After the electrolysis process, we get again new element 3 to 4% iron as a transmutation in yellow color bar, and significant increase of zinc is observed. This slides present the EDS results of bronze alloy. We performed the experiment at 33 volt with 5 ampere per centimeter square current density for 10 hours. Figure 6 provides the EDS results of pure bronze that contains mostly copper in blue bar and little tin in dark green bar. Figure 7 shows the EDS results of reacted bronze at location 1. We can see significant production of iron in yellow color with 16.3% and zinc in red color with 3.2% at location 2. Iron and zinc are 16.6 and 4.9 weight% respectively. At location 3, we also get transmutation as iron and zinc. Let us look at one more EDS results for solder alloy. We do electrolysis at 30 volt with 4.7 ampere per centimeter square for 10 hours. The left figure tells the EDS results of pure solder. The pure solder contains mostly lead, tin and arsenic. Here dark blue bar represents lead, dark green bar shows tin and arsenic in red color. Right figure shows the EDS analysis of solder after electrolysis. In blue color bar, there are 3.38, 1.27 and 2.98 weight% of copper at location 1, location 2 and location 3 respectively. We can clearly see the copper as the transmutation after electrolysis in it that is not present in the initial sample. Can electron beam interact with metal hydride to transmute element? In our experimental study, we use EDS, which uses an electron beam of energy 20 keV to check for transmutation products in the electrode sample to make sure that the transmutation products observed are not formed due to interaction of electron beam with the electrode sample. We synthesize a metal hydrides sample of magnesium nickel hydride as a control and characterize it using XRD. Now the metal hydride sample is exposed to a 20 keV electron beam from the EDS machine for 10 minutes so as to mimic the electron interacting with electrode sample during the elemental analysis. We then again analyze this exposed sample using XRD. This image shows the XRD results for the control sample before and after electron beam exposure. The black lines corresponds to XRD results prior to the electron beam exposure and the red line shows the results after. It can be observed that no new peaks show up after the electron beam exposure, which points towards the conclusion that the exposure of the hydrated metal sample to the electron beam used in the EDS analysis does not cause transmutation. It might be worthwhile to note that the hydrogen loading in control sample used is much less than the recommended loading suggested by Mercury for observing excess heat. Possibility of superhydride phase. As mentioned in the previous slide, studies by Mercury show that amount of hydrogen loading in sample is a key factor in determining the reproducibility of excess heat experiment. In the recent studies done by Vishwanathan and group, they have shown using what they call the pressure potential method that the formation of superhydride phases such as PDH10 are facilitated even at low pressure in electrochemical system. In this same line, we are exploring the possibility of superhydride formation in the electrode during electrolysis for the electrochemical system relevant to us, such as nickel cathodes in aqueous alkali hydroxide electrolyte using computational DFT methods. are the brass, bronze, solder, and silver brazing superhydrides formed in situ by electrochemical process stable at atmospheric pressure. To check for any possible stable superhydride phases formed due to electrolysis in the electrode, we conducted thermogravimetric analysis on the post-electrolysis electrode sample. From these results, we can observe that at around 900 degrees centigrade, the weight percent drops rapidly. This can be attributed to the decomposition of any potassium carbonate percent on the electrode sample, as potassium carbonate decomposes at around 900 degrees centigrade in nitrogen atmosphere. This leads to the conclusion that there are no stable superhydride phases present at atmospheric pressure in the electrode sample after electrolysis. Conclusion: light water electrolysis of alloys generate iron when copper is present in the electrode, like that brass, bronze, and silver brazing. Electrolysis produce iron in silver brazing and copper in solder wire. Brass produce iron with increase in zinc. Bronze also produce iron and zinc. Transmutation is not caused due to electron beam interaction at low hydride concentration or loading. TGA suggests that no stable superhydride can be prepared electrochemically at atmospheric pressure. Thanks.
We have some time for Q&A if anybody has any questions.
Is it possible that trace element contaminants in either the rods or in the electrolyte could be selectively brought to the top of the cathode or the anode, whatever you're analyzing with the electron diffraction technique, because I believe that analyzes only what's at the surface, which is a small amount, and the analogy I would use is a cracking distillation thing where it distills to the top a very special layer of a very small amount of hydrocarbon. Could it be some contaminants like that, and have you search for that?
And Monu, on your side, you need to unmute your microphone, please, so we can hear you.
Perhaps I can just answer. See, in the transmutation results, potassium we cannot take into account because that comes from the electrolyte. And in typical alloys, this near surface segregation is known in catalysis. We have discounted that. And we obsessively look for sources of contamination. We are very keen to know any such contamination. We have been very careful. As far as we can say, there is no contamination. I mean, we look at this fairly obsessively. Okay, so we have been careful about that.
All right, we have time for one more question.
Well, thank you very much for these interesting experiences, but I am a little bit surprised by the content in carbon before electrolysis. You have a lot of carbon in all your samples.
Carbon is, we don't take into account, yeah, we cannot comment much on carbon. We don't even consider carbon because it comes from contamination. Yeah, we don't consider carbon too. Okay, so potassium carbonate is there in the electrolyte. So one source is that supposing we dip the electrode and we do wash the surface with some water, but still there might be some carbonate. I mean, so carbon, potassium, these are not anything of interest with respect to transmutation. I mean, so what he indicated is outside of carbon, outside of potassium. So those are the things which he pointed out. Sure.
Excellent. Thank you all very
Sorry,
much.
I'd like to say one word, please, because the goal of this project was to prove that alloys are producing transmutation. So should be able to have a control with material without alloys and compare them. Thank you.
Which we proved last time in the ICCF23, which is being published probably any time now.
All right, everybody, thank you so much for your time. Appreciate it.